Here are some quick notes on convection to accompany Chapter 6 of To Build a Star. So we saw already in the textbook that convection can occur in the presence of a steep temperature gradient that will define or that will cause convection to occur, and that's defined by the Schwarzschild criterion. And there was a nice derivation in the book going from the fundamental thermodynamic relation and saying that if you don't want convection to happen, you need the entropy to increase with increasing radius. But interesting question is, what if there's also a composition gradient? So we ignored that. We basically assumed that there was a homogeneous composition. But what happens in that case? Well, still, convection still sets in when entropy decreases with increasing radius. But what we have to do is we have to go beyond the fundamental thermodynamic relation used in the book and To Build a Star, and we have to include the change in internal energy that occurs when you change particle number. And so you have your chemical potential and change in particle number that can also change internal energy. And so energy can change, right, with changes in composition. And so what you need to do is you basically rework through that derivation, and what happens is you generalize to something called the Ladeau criterion. So we still have the Schwarzschild criterion with this business here, but then there's a correction for the change in the chemical potential with the change in pressure. And so what this means is that if you have a negative composition gradient, so what I mean by that is if you have light elements on top of heavy elements, then this increases your stability to convection, and so that you can support higher temperature gradients. So where will you get light elements on top of heavy elements? Well, near a nuclear burning layer in a star, right? Burning is going to create heavier elements, and there's going to be lighter ones on top of that. You also have this occur in accreting white dwarf and accreting neutron star systems, where you dump hydrogen and helium onto a surface of a neutron star that has heavier elements from previous nuclear burning cycles. And when you want to calculate, the onset of convection, you need to use this more general form, this Ladeau criterion. Okay, so one thing that you may be curious about is what are the scales for convection? We know that there's some kind of mixing going on, but how big is the circulation that's going on? Like how far is an individual blob moving? How fast is it moving? How long does it take to go? That's something you may be curious about because it's interesting. And the honest answer is that if you want to do it properly, it requires a 3D treatment. It's extremely complicated. Use some back of the envelope estimates, and that'll give us the rough scale for how these things occur. So what's often used is something called the mixing length theory that Prandtl developed. And the mixing length, it's sort of like the mean free path in a sense. So it's the distance that our blob that's being convected is going to travel, vertically until it dissolves into your surrounding environment. Okay, and so this mixing length approximation is often that the mixing length is equal to the pressure scale height times some constant. And this pressure scale height we derived in exercise 2.2 of To Build a Star. So you'll remember this is the height that you have to travel in an isothermal atmosphere for the pressure to reduce by a factor of 1 over E. So we solved this previously. Obviously, this is going to be a poor approximation where you have a very large temperature gradient. So, for instance, near the very surface of your star. But nonetheless, we often take this alpha constant that scales the pressure scale height is usually on the order of 1, and we solve this back in exercise 2.2. So it depends on your local temperature, it depends on your local composition, and depends on your local gravity. And so the neat thing is this is only dependent on all local quantities. You don't need to know anything else about the rest of the structure of the star. So if we plug in some numbers for our solar photosphere, our mixing length is something on the order of 100 kilometers or so. So, much smaller than the radius of the sun. So it's relatively small, but still, it's quite a large distance for a blob to travel. If you go halfway towards the center of the sun, then you get a mixing length that's on the order of 10 to the 8 meters. So it's something like 10% of a solar radius. The one thing I want to point out is that the boundary where convection kicks in the sun is actually around 3/4 of a solar radius, but still you get the kind of rough order of magnitudes. Something like 1/10 of a solar radius is how far these blobs are traveling in convection. Obviously, this approximation all breaks down if you go to somewhere where there's technically kind of infinite gravity, right? Your g when your radius goes to 0. So for the solar core, this goes to infinity, and it's not particularly useful. In practice, what's done is the mixing length is typically calibrated to one of two things. Either the standard solar model, so this is part of why this solar modeling problem is so important. You know, the helioseismological and the stellar models that are compared to photospheric observations, the fact that they don't agree on the structure of the sun, that's a problem because we need the standard solar model to calibrate our mixing length that we use to calculate the properties of basically all the other stars, right? And for stars that are not the sun, you use 3D calculations, and these are benchmarked to the standard solar model. So we need to understand the structure of the sun. And we can take a look at a calculation of the sun. So this is the mixing length divided by the pressure scale height. So basically gives you this alpha coefficient. And you see for this model, we're looking as a function of radius. So the effective radius is as a function of the pressure. Effective pressure is the pressure at the surface of the sun. And you see, you're on something on the order of 1, almost 2. And then it just doesn't work great as you get close to the surface of the sun because the isothermal approximation is not very good. Okay, well, how fast are these blobs moving? So what's the convection velocity? So what we have to do is just consider the amount of energy that a blob is transporting. So this is going to be, or really that convection is transporting. So we're basically going to consider we have an upward moving blob and a downward moving blob. So the luminosity that is being emitted by your star has to be carried out by convection in a convective region. And so this luminosity is going to be equal to the rate of energy being carried upward minus the rate of energy being carried downward. And this is going to be positive. You're going to carry more up than down because your star is shining. So the energy that's being carried is basically a kinetic energy, right? So we have some number of particles with some kinetic energy divided by the temperature. And so there's an upward blob and a downward blob. So then we can convert this basically to a velocity that we have here. Instead of having an absolute number of particles, we're basically going to take a number density and multiply it by a volume. So we have an area times the length part of the velocity. That gives you a volume, and you multiply that by the number density to get you this capital N. So that's the trick that we played there. Because we're talking about blobs that are moving the same speed and of the same size, we'll pull all this stuff out front, and we just are interested in the temperature difference. So what's the temperature of an upward moving blob versus a downward moving blob? For the area, we're talking about basically a spherical shell here, so we're going to use 4 pi r squared for our area, and we can plug that all in. And the last thing we want to do is, instead of number density, we're going to work in terms of a mass density and a composition, because that's typically what you're considering in a stellar calculation. So we can plug in the numbers for the sun. So we have a solar luminosity. Again, let's just take as a rough check halfway through the star, so half of a solar radius. We find that the product of the velocity and this temperature difference is 100 meters per second Kelvin. So we're going to get to a velocity here in a moment. We have to get another equation, right? We have 2 unknowns, so we're going to need to get a second equation to solve this. So what we're going to do is we're going to consider our blob as a buoyant cylinder, so kind of like a helium-filled balloon. Once you release it, right, a helium-filled balloon, it reaches terminal velocity, and that terminal velocity is basically what we're interested in here. That's that convective velocity. So that's reached when the net buoyant force, so really your buoyant force, I guess I should say minus gravity, when that equals the drag force. So when your forces are balanced, you'll no longer have acceleration, you'll be at some constant terminal velocity. So our upward force we have the buoyant force, so the density of the fluid times the volume of the object times g. We have to subtract the gravitational force, so this is going to be the mass of the blob. Bigger blob weighs more, gravity's pulling downwards. And so your upward force is going to be your local gravitational acceleration times the volume of your blob times the difference in density between your object and the fluid. And the object, the blob, is of course going to be less dense than the fluid because it's rising. And for reasons you'll see in a moment, we'll break this volume into an area times the length. So the drag force, one hand way to think about this is right as a force is just a work over a distance. One definition of work is the change in kinetic energy. So we start out with some initial kinetic energy, and then it's basically all removed. That surplus that we had to get to the terminal velocity. So then this kinetic energy is just 1/2 mv squared, and we're going to divide by a distance because we have work over distance to get a force. And so then when you do 1/2 mv squared over a distance, that can be written as 1/2 rho v squared times the area. So this is going to be the density of your fluid times an area, and you do that so that you get 1 over length here. And so these two have to be equal to each other. Your upward has to be equal to your downward, so you set them equal to each other, and you can see now why we wrote area times length. These two things cancel. And you get that the velocity of your convective blob is square root of 2 times little g, the local gravitational acceleration, times your mixing length, times the ratio of the density difference divided by the density of the fluid. Now, we had this equation up here where our two unknowns were the velocity and the difference in temperature between the upward and downward blobs. So we want to get to that unknown, so we'll take advantage of the fact that this is an ideal gas, and the pressure of the blob that we have is the same as the pressure of the environment. So we can do a substitution in and put delta T over T instead of delta rho over rho. And so if we can solve these two equations, we have our two unknowns, two equations, you can go ahead and solve that at this 1/2 of a solar radius as a kind of benchmark. And you see that the blob is moving at 100 meters per second, which is not all that fast if you think about it. It's like 200 miles an hour. And the difference in temperature between the upward and downward blobs is only a Kelvin, right? It's kind of remarkable how small that temperature difference really is, and yet this is effective at carrying away a whole bunch of energy. So what kind of time scale does this occur on? How long does it take for your blob to rise or to circulate? So, we have a velocity and we have a mixing length. So the convective time scale, right, is just the length over the velocity. You get around a week. So it takes around a week for your blob to go up, and it'll be about a week down. So you're talking about on the order of a week or so, 2 weeks, for this blob to circulate, if you want to think of convection that way, which is kind of amazing. It's not all that fast, right? Why do we care about this? Well, note that your convection time is much greater than the dynamical time, right? The dynamical time for the sun is about an hour, and that dynamical time tells you how long it takes for basically structural information to propagate, so a sound wave to propagate, or an object to fall under free fall. And so since the convection time is much greater than the dynamical time, then hydrostatic equilibrium still applies even for your convective regions of a star, which is good because we rely on that for stellar structure. So now let's consider a more exotic scenario just for fun. These objects, there's a thing called a Thorne-Zitkov object, or Zitkov, and it's hypothetical. So there are some candidates out there, but it may well not exist. And what it is it's a neutron star inside of a red giant. So this is a hypothetically stable object. One major issue is how you form that to begin with is a tricky part. But supposing you form it, this is a stable object. And what you basically have is you have a neutron star. On the surface of your neutron star, you have nuclear burning going on because material from the envelope, basically from your red giant, is accreting onto the surface of the neutron star. You get nuclear burning, and then there's a big convective envelope here. And so here, the luminosity is much greater than the solar luminosity. Surface gravity is much greater here as well. And so your velocity is more like 100,000 meters per second, much faster. This is still orders of magnitude less than the local sound speed, so hydrostatic equilibrium still applies. And the mixing length here is quite a bit smaller, you're something on the order of a kilometer. Again, you can calculate your convection timescale, and that's on the order of 0.01 seconds. So why is that interesting? That's because that's comparable to the beta decay time for the nuclei that are synthesized in this hydrogen and helium burning here. So you have hydrogen and helium burning, you produce proton-rich nuclei in a similar way that you would in the rapid proton capture process on accreting neutron stars and also accreting white dwarfs. But since this time scale is comparable, what's happening is you're producing these proton-rich nuclei and you're convecting them upwards and often back on a similar time scale. So what you have is something that's called the interrupted rapid proton capture process. So if this is our chart of the nuclides, proton numbers vertical direction, neutron numbers horizontal, the gray boxes are stable nuclei, the arrows connecting boxes, these indicate your nuclear reaction sequence. This looks a lot like the rapid proton capture process that you may have seen in this class before for accreting neutron stars, but you're often dealing with nuclei much closer to stability. And the path is different because you're basically synthesizing proton-rich nuclei and then taking them away from the proton-rich environment so they have time to beta decay to get closer to stability, and they can proton capture again. That's kind of cool, and these sorts of models are how you come up with abundance predictions for the surface of a Thorne-Zitkov object, and those abundances are basically how we have TZO candidates. So other than that, there's no direct information. So these may or may not exist, but in any case, it's kind of interesting. So apologies, this video is a little bit longer than usual, but I am done now. So that is it for these quick notes on convection.